Alright, so I told you that we would talk a little bit more about plate boundaries. And so you're going to use the outline that I've provided for you and fill in the 3 types of plate boundaries, the type of plate movement that goes along with that, and any examples that I happen to give you of real-world locations and features that are created. So this video is called Plate Boundaries. So let's take a look at the 3 different types of plate boundaries. The first type of plate boundary is called a divergent plate boundary, and the plate movement itself is called tension, where the 2 plates are pulling apart from each other. And you'll see my simple drawing of 2 individual plates that are going in opposite directions of each other. Examples of where this is going to occur is the Mid-Atlantic Ridge, with the North American plate is moving away from the Eurasian plate and the South American plate is moving away from the African plate. This is an example of where we see sea floor spreading, which we talked about in the earlier video. That's underneath the ocean, on the ocean floor. We can also have divergent plate boundaries on land, and an example would be the Great African Rift Valley, where we've got a 2 plate boundary, or 2 plates that are pulling apart at a particular boundary. So here's a simple example of what a divergent plate boundary may look like. You have the magma in the mantle, and again, the convection currents are the driving force that are going to push that magma up through a crack in the crust. And when it does so, it's going to cool and then push the plates apart that are already in existence. This is a divergent plate boundary. The second kind is called a convergent plate boundary, and a convergent plate boundary has compression plate movement or colliding. An easy way to remember, they all start with C: convergent, compression, or colliding. Now, in a convergent plate boundary, the density of the plate is going to dictate what occurs. So you have ocean-to-ocean plates, you have a continental plate colliding with an oceanic plate, or you have a continental plate colliding with another continental plate. My suggestion would be to pause this to fill in your outline. Remember, it's all about the density. The more dense that particular plate, it's going to go under or subduct under the less dense plate. So that's going to result in a wide variety of examples. I've given you the movement, I've given you the types of plates that are colliding, and I've given you particular examples. So pause the video to fill in your particular piece for convergent plate boundaries. Here's an example of the oceanic crust to the continental crust. So we end up having the subduction of the more dense oceanic crust back down into the mantle. And when it does that, it forces the magma upward and creates the continental or the coastal volcanic mountain ranges. Here's a picture of an oceanic to oceanic convergent plate boundary, where the more dense oceanic crust is going to subduct under. The same thing is going to happen, and it's going to force the magma upward, and then eventually it reaches the surface and cools, and it creates a volcanic island arc. It's not on the continent because this is going to happen with 2 oceanic crusts. The third kind is continental crust coming in contact with continental crust. Both of them are going to be less dense, so they're going to force upward, and they're going to cause that rock to kind of fold and break and produce a mountain range. The example would be the Himalaya Mountains. When India collided into the Eurasian plate, it produced continental mountains. The third type of plate boundary is called a transform plate boundary, and the plate movement is going to be what we call shear movement. The plates are going to simply slip past each other in opposite directions. Most of the world's earthquakes are going to occur at any of these plate boundaries because we have constant forces and the energy has to be released. But typically when we think of an earthquake, we think of a transform plate boundary because that's exactly what we find in California. The San Andreas Fault is on a transform boundary between the North American plate that is moving north and the Pacific plate that is moving south, and they are simply slipping past each other. Here's a great picture to kind of show you the relative movement of the Pacific plate, and I said that wrong. The North American plate is moving downward while the Pacific plate is moving upward, slipping past each other. Make sure that you have all of the blanks filled in your outline, that you've got your plate movement, and you have your examples. Ladies and gentlemen, that's a wrap.